Morning, everyone. I'll quickly revise a couple of things about AES that we have seen last time. Uh, so, advanced encryption standard is one option for DES algorithm that we are implementing right now in the practical examination, practical sessions. And why was this option made available? Because the DES algorithm was compromised. This is another block encryption, which follows the Feastel function and all these things. And still it is secure because there are a couple of reasons. One reason being, this substitution byte step is a quite extensive step. The S box which is used is quite extensive, and the logic behind that design of S box is not known, so it is still secure. And the second reason is the key size. The key size is very large. 128 bit is the minimum key size. 256 bit is the maximum key size. So even if you think of trying all the combinations, it takes really bad time for any computer to break those many number of keys. Okay, so this is just an overview of AES, and what happens in AES is you have many rounds, 10 rounds, 12 rounds, and 14 rounds. Each round, there are 4 steps. You have to use a substitute byte, shift rows, mix columns, and the XOR with the key, whatever the key which you are using for that particular round. Okay, so there are 10 different keys which you will need for each round, and the keys will be generated by a key generation algorithm. Okay, and this is the encryption and this is the decryption. In the decryption process, the rounds are reversed, not the keys are reversed. Okay, so that is these are few things which we have learned in the last session. This is a quick review of what is happening in the round itself. Okay, so what happens is whatever the matrix you have, okay, the matrix is represented as a state. Okay, so first row, second row, third row, and fourth row likewise. In the substitute byte, what you do is you take a byte from that matrix and you choose the particular entry in the S box with the column and row, and you choose the entry from the S box and you prepare the new matrix. Okay, so that becomes a second step. Sorry, input for the second step. Then in shift rows, what you do is some of the data is kept as it is. The first row is kept as it is. The second row gets shifted by 1 position. The second row gets shifted by 2 positions. The third row gets shifted by 3 positions or 3 bytes left. Okay, so this is how the transformation takes place. And as I have told you, some of the bytes, when you are shifting it 3 bytes left, it is as good as shifting 1 byte right. Okay, so these are the positions of the bytes. If you go, if you spend some time on this part, you'll come to know what are the meaning of these arrays. Okay, so the first row is kept as it is. There is no change in the first row. Okay, and then the other positions are changed, right? So the new matrix is prepared after shifting those bytes. And then the third step is mixing of columns. Now here in the mixing of columns, what you do is there is a product of one matrix and the particular row is taken, and the product is prepared as an output of this step. So this multiplication also we have seen last time, which was the matrix used for the multiplication during the encryption, and which was the matrix used for the decryption for this step. And then at the last, whatever the key you have got, the sub key. Okay, what you have to do is you have to get the sub keys from the key generation algorithm. So once you get the sub key, you have to XOR that sub key with the data you have got from the multiplication mix column. So this will be the output of one round. Okay, and these rounds are repeated for 10 times if your key is 128-bit key. If the keys sizes increase, the number of rounds are also increased. Okay, so this is what the bigger picture of AES that we have seen up till now, and we have seen these steps in detail. If you remember, substitute bytes, shifting of rows, mixing of columns. So this is the matrix multiplication that we have seen. This is the reverse or inverse mix column, which is used for the decryption process. And this is fixed. Okay, whatever the state, because this data will be different for each round during the encryption, during the decryption. Whatever the data you get, you have to multiply that data with this fixed mix matrix. Okay, so that is one thing you can. And then the last step is to XOR the data with the key. So this is what we have seen up till now. Actually, AES is divided into two parts. One is the substitute layer, where we are substituting some data with the original data. Okay, but we are maintaining that track, what we are substituting with the S box and inverse S box. Now, the second part is the diffusion layer. Okay, if you remember the start of the encryption process before we started TES, AES, and so on, there were three types we have seen. One is the substitute cipher, the other one is transposition cipher, and the next one is the product cipher. So this is a product cipher where we are using the diffusion layer, or you can say a transposition layer, where we are changing the positions of the bits. Okay, when we are executing this mix column, then we are actually changing the positions of the data. Okay, so this is just another review of what is happening in the AES. Right. There are some advantages. One more thing I forgot to tell you. It is the same algorithm is also called as Rendell algorithm, because it was designed by Rendell, AES, and it is very speedy, and it converts the block very quickly into a cipher, just because you are not spending time in compressing the data, in expanding the data, and so on. So it is much faster than DS, because in DS what happens, sometimes you are expanding the data, sometimes you are compressing the data, and that is just adding the complexity of the execution. But here AES is performing quite quickly. It can be implemented on the smart cards which we are using right now in day-to-day life. It can be implemented directly on the ATM cards. the smart cards which has the chip inside it. So there are multiple uses, and these are few more advantages. You can go through it a bit later. Now there are some limitations. Uh, these limitations are actually the limitations of the what we can say, a block cipher. Okay. Now, before we understand the limitations of AES, I want to go back to the topic which I have skipped uh, last week. Okay, so I'll revisit again these limitations once we see all the topics that we have skipped. Let me just yeah. So these are the modes of operation that has to be understood first. Actually, if we see the flow of the syllabus, the modes of operations appear first before the AES and DS. AES and DS are the last topics of this unit 1. But I wanted you to understand application as such first, and then you can understand this theory based on that application. So this will become very easy to understand if we would have conducted this session earlier. It becomes a very it would have become a bit boring as well as critical to understand. So let us try to see what are the operating modes of block cipher. Now, the name itself suggests that you are taking a bunch of bits at a time, and then you are encrypting those bits. So what is the first mode? Electronic code book, ECB mode, then cipher block chaining mode, feedback mode, counter mode. Now, what are these modes? Actually, this is the way of executing the rounds, how you are giving the input to a round, how you are getting the output from the round, and so on. Okay, and how to make the process bit difficult for the hackers to do the crypt analysis of that algorithm. So let us say first, that is electronic code book. What happens in this electronic code book is, let's say you are designing some algorithm, encryption algorithm. It's a very simple thing. You give the block of plain text to that algorithm. You use some key and you produce a ciphertext. Okay. And this process has to be repeated for all the number of blocks you are preparing. What happens is, in a file that you are encrypting, or in any data that you are encrypting, what happens is you have to create the blocks, and this process will be repeated for each block. Okay, so this is a very simple operation mode. Okay, and during this decryption process, the decryption algorithm is used instead of encryption algorithm. The ciphertext is provided to that decryption algorithm, and you are producing the plain text. And you are using the same key at all the time, because this is a what we can say, symmetric key algorithm. Whatever the key you are using at the encryption, the same key will be used at the decryption. Okay, that's why it is called a symmetric key encryption. And both the algorithms, DES and AES, are a symmetric key algorithms. Okay, so now, why it is called as a code book? What happens is, let's say this is a data which contains XYZ something, and for that XYZ plain text, if you use the same key all the time, you'll produce a particular ciphertext. Okay, let us say here the plain text is PQRS. You're using something, and obviously some ciphertext will be produced. Now what happens is, for some input you are getting a particular output. Okay, so you are creating a what you can say, a database where there is an input and there is an output. Okay, so it's like a code book. So that's why it is called as electronic code book. Now, can you please spend few seconds on this diagram, and can you tell me what is the problem in this method? Actually, we are trying to understand. I just skipped the limitations of AES. Okay, so to understand the limitations of AES, we should know, to understand what are the problems of these methods. Okay, so I want the answer from you, that what kind of problem you find in this method.
There is no sharing of the key or communication between the various levels of encryption.
I'm sorry, your voice is bit low.
There's no communication between the various levels of encryption. So you don't know what the previous encryption has done.
Okay, okay.
And the encrypted ciphertext is less than that the ciphertext which is going to be decrypted.
No, actually, yeah, just don't look at the number of blocks here. Just assume that they are same. Actually, the same ciphertext is provided at the decryption part. So it is not like you have to provide a different ciphertext. So don't look at the number of blocks given in the picture. If you remember, like, if I'm typing the word, the word, more often in my text, okay, or you might have observed some, typical words that people keep talking about, and what happens is, if you provide that word as a plain text and do the encryption, every time you do that, you'll get the same ciphertext. Okay, so for the hacker, if he knows that this guy speaks about this word quite often, or if it is a bank who is doing the transaction, the account word will be used as quite often, then if you are getting the similar ciphertext at regular interval, you'll come to know that account word is getting uh, into this converted ciphertext like this. So this is the ciphertext for that particular account word. Okay, so it becomes very easy for the hacker to know what could have been the plain text, even if he doesn't know the key, or even if he doesn't know the what process is used for encryption, but he might know that, he might come to know that this is the ciphertext and this is the plain text. Okay, so that is the problem of ECB, and that is why the next mode is used, that is cipher blockchain. Okay, now what happens here is, there is one term which is used as an initialization vector, that is IV. Okay, now this is a random data which has to be generated by the algorithm, okay, encryption algorithm. what you have to do is a plain text has to be, whatever the first block you are encrypting, that has to be XORed with the initialization vector. You might have to prepare the IV or initialization vector as same with the same size of the block, okay, so that you can do the XOR operation. And whatever the XOR operation you are doing, that will go to the encryption part. Okay, now you are using the same key here. The only problem is whatever the cipher, not the problem, only the solution is to the problem that we have seen in the earlier method. This ciphertext will be the initialization vector for the next round or the next block, not the next round, the next block. Okay, so instead of XORing it with initial vector, you are XORing it with the ciphertext from the earlier block. Okay, and this chaining is to be performed until you get the last block. Okay, so this, what will this do is, even if you are providing the same plain text consecutively, just because of the two different XOR inputs for the two steps, you will get this different ciphertext at both the steps. Okay, so this will reduce the problem of ECB, and at the time of encryption, what you have to do is you have to for the first decryption, you'll have to XOR the converted encryption with initialization vector to produce the actual plain text. Okay, so this is the exact reverse process for the decryption, and you are providing this ciphertext, whatever you are getting the ciphertext, to the next round for the for getting the actual plain text. Okay, so this way you have to do in the encryption and decryption. Any doubts here? And as we are chaining the ciphertext, the name of the method is cipher blockchain. Any doubts here? Okay. Now, what is the disadvantage of this? A parallel operation cannot be performed. We already talked about the advantages because it doesn't produce the same ciphertext for the same plain text. Now, you cannot perform these actions parallelly. Okay, so it might go slow. This method might go slow because even if you are doing a encryption on blocks by block, then next block cannot be encrypted because it depends on the output of the first block. Okay, the parallel operation is not possible, so it becomes a slow process. Okay, and if at all, if you miss any block, or you'll not get any actual original message. Okay, so that is the problem of this CBC mode. Okay, now how to resolve these problems, that will be seen in the cipher feedback mode. Now, what happens in cipher feedback mode? So what we are doing is we are trying to see all the modes of operations and the problems of each operation, and in the next method, the earlier problem is getting solved. And DES and AES have used multiple, what you can say, multiple modes of operations, so that they get the advantages of all the methods that they have chosen. Here, just look at the method here. What we are encrypting is completely different. Okay, we are not encrypting the actual plain text. We are encrypting the initialization vector here. Okay, so encryption algorithm is encrypting the initialization vector using some key. Okay, whatever you are getting as an output of this method or this step, that will be XORed with the plain text. Okay. Now, here we are not keeping the size of the initial vector as same as plain text. So the problem here was the size of the initialization vector and plain text was the same. So if a hacker gets the hold of IV randomly generated data, then it becomes easy to know what is the block size and all these things. So here that problem is resolved by choosing some different size of the IV, different size of IV, and what you're doing after encryption of IV, you're just XORing the plain text with the ciphertext. Okay, and then this is provided to the next block of the encryption. Now, what is the problem here? Not the problem, the situation. We have to get a separate IV for the next round. Okay, now we have a ciphertext here. So what we do is we have to shift, we have to prepare actual size of the IV. Let us say this IV is 100 bits. Okay, but the plain text is 64 bits only. Okay, so obviously from the 100 bits, you are discarding some of the bits. Okay, let's say 36 bits are discarded. The ciphertext which is getting prepared, which is getting ready here is also a 64 bits. But with this 64 bits of ciphertext, you cannot prepare 100 bits. Okay, so what we have to do is whatever the discarded bits from the first IV, first encrypted IV, those discarded bits are used to prepare a new IV in the next round. Okay, and the same process will be repeated all the time. Okay, now here we are actually adding the one layer of security. Can someone just tell me something about what you have noted difference between cipher blockchaining and cipher feedback mode? What is that extra level of encryption? Okay, so extra level of encryption is we are, securing the IV. That is very important because if the initialization vector gets compromised, okay, there are two things. One is the key which you have to keep a secret because the same key will be used by the decryption guy. Okay, so let us say you are sending some text to your friend, a secure text. When you are sending the secure text, you'll also have to send a key along with it, or maybe in a separate communication, because otherwise the receiver will not be able to decrypt this without that key which you have used for the encryption. Okay, so this key has to be transferred some way with the receiver. Now the same thing is happening with the initialization vector. This IV also has to be sent along with the key, because again this is needed for the decryption. IV is used here and IV is used here, right? So the problem is if the key is compromised or the IV is compromised, then you are losing the security. So at least what we can do here is we are encrypting IV so that the initialization vector gets secured, and whatever the process you are doing will have one additional method of or one additional level of security. Now the same thing will be used for the decryption part. Okay, so IV is encrypted and some of the bits are discarded. Then ciphertext will be XORed with this IV to get the plain text. Okay. Now the problem with this method is whatever this cipher feedback mode is, if you find any bit error, a single bit uh, change or single bit missing will hamper all the encryption process or decryption process. Okay, so that is the one big problem of CFB, and you have to be very sure that you are doing all the operations very correctly. Now, why we are talking about this? Because the encryption is not only used in the programming. Now, whatever the encryption is used in a day-to-day life is, it is hard-coded on the chip. It is embedded on the IoT devices which you are using nowadays, and these are these has to be embedded in chips, hard-coded in the chips, and all these things. So you have to be very sure while working on the bits, and you must be knowing that if you are using a chip, there are multiple pins of ICs, IoT devices, and all these pins are connected in some way. And if you lose a single connection, then these kinds of bit error occurs. So you have to be very sure that no such bit errors should hamper the method that you are using for the encryption. And because of these problems, now we are moving to the next operating modes, that is output feedback mode. Okay, let me give you the what is happening here. I hope you have understood all the concepts that we have seen up till now. Any doubts?
So can you once again explain how do we secure the IV?
IV. Okay. So if you have noticed in CFB mode, we are not encrypting the plain text. Okay. The encryption method is or algorithm. Okay. Let's say you are using DES or AES, that actually algorithm is encrypting the IV directly. You're not encrypting the plain text. Okay. So in this method, you are actually securing the IV, and then whatever the output of the secure IV, that is XORed with the plain text. So actually, whatever the output you are getting, that will be the mixed cipher text of the plain text and encrypted IV.
Okay, so yes, I got it.
Right. So in previous examples, what we have done is we are XORing plain text with IV. So here IV is not secured, and whatever the output you are getting, then you are either encrypting or decrypting the data. So actually you are encrypting the plain text, not the IV here. But here in CFB you are encrypting the IV, and at the end obviously plain text will be encrypted automatically. So the next one is output feedback mode. Now, one problem that we have discussed is not cited yet. In fact, I was expecting that question from you. That we have discussed the problem that in these methods, the feedback mode or chain mode, the parallel operation is not possible, right? So how to perform this operation parallelly? That is one thing that has to be addressed. So output feedback mode solves that problem. What we have to do is, here, instead of initialization vector, what we are doing is we are using nonce. Does anyone know about nonce? It's a mathematical term, if you have heard of it. I guess no. So
Not a number.
not a number. It is a number.
Is it? Uh,
But something related to a number that, you know, you're going in a correct direction. It is a number which is used only once. Okay, that is nonce. That means what? The initialization vector in earlier cases, you have to use initialization vector along with the key, same key, for multiple kinds of encryption, and you might, you know, get compromised with the IV or the key. Here, if we are using nonce, the whatever the random number you are using here, don't use it any other time. If you remember the stream cipher one-time pad, so it is the same concept. One-time pad, whatever the key you are using for conversion, you are not going to use that particular combination of bits. Never you'll use at other encryption time. So the same concept is used here. Another concept, the same process, you are encrypting that nonce with the key, but instead of providing the actual ciphertext for the next round, what we are doing here is the encrypted nonce with the key is provided for the next round. Okay, so all this process, this dotted square block can be performed parallelly while you are, you know, actually XORing plain text with the output of each round. Okay, so whatever the ciphertext you are getting, that can be performed, that can be executed parallelly with some data execution of this nonce encryption. Okay, so this is the encryption and this is the decryption. The actual process is same. See this, the block is repeated here with nonce key and the encryption process. This is same. The only thing is, instead of providing P1, you are providing C1 or ciphertext block 1 for the encrypted one. Okay, to produce the plain text. Only this is the difference between encryption and decryption. Now you are, you know, trying to solve few things of the previous methods. Now again, if you talk about the communications which is happening any given time nowadays in the world, you know, you take any right now, you think of how many devices are communicating securely with how many other devices in the complete world. Okay, you'll not be able to find out the actual number. Okay, and if you are, you know, thinking of creating such numbers which can be used only once, you know, you will, you know, go short of those numbers at some moment of time. So that is the problem of the earlier method. So that's why it is the next method is explained over here, the counter method. Okay, now what counter method does is, you can execute these parallelly. It actually, you know, reduces the processing time so quickly, because if you are encrypting let's say 50 MB file, okay, and if you are creating the blocks of 64 kilobytes, okay, one block of 64 kilobytes, you think of how many blocks are prepared of 50 MB, and this process you cannot uh, do it parallelly. Okay, so in the previous case, you are reducing the time by half, but this is again is happening in a chain mode. Okay, so that cannot be done parallelly. But in the counter method, you have to create multiple nuns. Okay, multiple nuns, and these counters, which are called as counters, and these counters can be repeated. Okay, so the only thing is, in one process these counters are not same. Okay, these are actually numbers which are used only once in this method. So you can have but this counter one can be repeated at the other places. Here the same encryption we can achieve with more or with faster processing. Okay, then there are multiple other methods, XTS AES mode. We actually have seen this AES mode where you are not just encrypting the counter, okay, but you are encrypting the plain text as well. If you remember, in the previous methods, we are just encrypting the initialization vector, nuns or counters, okay, but not the plain text. You are just XORing that data with the plain text. So just to add one more security level, what we are doing here is, in this XTS AES mode, we are uh, applying encryption on the uh, counter as well as the plain text. Okay, and the XOR operation is happening at multiple levels. Okay, and whatever the ciphertext you are getting, it will be more secure. Okay, so this is a per block encryption what we are applying here. At many other, what you can say is, these are the sub keys which are getting generated at multiple levels. Okay, so you have to use multiple keys, then sub keys and all these things, okay, to produce the secured ciphertext. Okay, and then you have multiple levels of XTS. This is just a overview. This is not there in your syllabus, but I have kept this just for you to understand how the encryption can be made more complex for the for the hackers to do the cryptanalysis. If you have any doubts up till now, please note those doubts, and you can keep asking me while I'm just going through these slides. These are some of the advantages of XTS AES. You can go through these bit later. And we have seen actually fiscal ciphers and DES, AES up till now. So actually, we have completed the this unit 1 in the first 2 weeks. Please let me know just a quick feedback if you are understanding all the concepts, because we are going a bit faster.
Yes, understanding.
Yes, sir.
Okay, thank you. But I'm still not, I still want some queries from you, the doubts from you. It is not possible that you'll understand everything. Okay, so let me stop the presentation here. Okay, the today's lecture session is over. Just a minute. I want to announce one thing here. I'm working on drones, and I have couple of drones project. I'm not sure if you have decided your project, capstone project, or anything else. But if you are interested to work on the drones, be it a capstone project or be it something else, apart from the capstone project, please let me know, because I have couple of really good ideas. Right now, I have my MTech student who is working on anti-drones technology. We are trying to develop some technique or method for hacking into a drone and controlling a drone from like maybe there is a enemy's drone, and how to control that enemy's drone by some method that we are trying to work on. This is for the defense, obviously. And if you are interested, I'll have to take few interviews, and then we'll process ahead. But that's the announcement that I wanted to make, and I'll be sharing the attendance link in a while. Okay, that's the attendance for you, and we are stopping here. If you have
So
any
what is the
doubts,
prerequisite for your that anti-drone project? What do you expect us like from us to know?
Prerequisites, he's saying.
So basically, I want to understand your background, how your thinking is, how your programming is, and whether you are interested in doing something in security, encryption, ethical hacking, or something like that. So you should know about these things, and you should have passion, compassion. You should be compassionate about anything. If you know the things which are happening in our university, there are some what you can say, many groups are there, student groups who are working on many areas. You must be knowing all those robotics areas, then hyperspectral areas. Actually, there are many labs which have been developed at our university. If you know about those activities, if you want to spend your time, doing these activities on many projects, then I want to know these things if you are interested. So that's what I will see.
Yeah, okay, sir.
Okay. If you have nothing to say, you can leave these sessions. I'm just staying in the room for some more time so that if there are any queries, I can answer.
Sir.
Yeah.
You can always use a node MCU to jam the drone. I mean, but this would like make it fall out of the sky, technically, like the opponent's drone or
Mhm.
the enemy drone, whatever it is. You can, I mean, if you want to control it, then I don't know what to do. But if you want to jam it, I guess the node MCU chip can be fitted on with a type of small power bank capacity, and
Right.
it can fly up. But your connection to your own drone needs to be secured in a different way, or a
Right.
stronger PA2 or WPS connection. I guess I don't know the name right now, but
Right.
if you configure your hard set into some different kind of a Wi-Fi or a connection, and the
Mhm.
other drone is just basic one, you can at least jam the drone and make it fall. And so
Yeah, yeah. So basically, anti-drones have multiple methods. You can use the radar, which can, block the drone's communication or drones
yes,
to fly, and or there is a physical attack that you can do on the drones. For these are some of the anti-drones techniques. We are specifically working on how to control the other drones which for which you don't have the controller with you. For that, there are many things that you have to study. This is a kind of new method that we are trying to know what are the things. So
sir, I have a question. So
yeah.
this is kind of similar to like the IR blasters and MI phones or something that can control ACs and stuff, or
Right.
these even in car keys. Like there's a new method right now going on, like car hacking. People just hack into your car by like physically. It's not really
Hmm.
hacking, but it is a hacking.
Correct.
They'll just with that same frequency, they'll hit the key, and whatever car you have, be it a Mercedes as well, it's going to be unlocked by that
Hmm.
person, for example. Or just connecting to that frequency, you're saying. So there's a lot of things, like there's even these TV remotes you get on the internet that actually just hack into any random TV and can change channel, screw around with the volume or something. And
Mm-hmm.
so there are these products out there. So is this any way related to like what the drone can do? Like
Yes, actually, see, drones uses the frequency obviously for the for communicating with the controller. Let's say you have a remote and you have a drone, so obviously you'll need some frequency, either 900 hertz or 2.4 gigahertz or 5 gigahertz, depending on what frequency you are using. Now, how to hack into the frequency and how to hack into the communication, that is the thing that we uh, are looking at.
But the bigger challenge is, even if you hack in, how do you stop the other person from actually shutting it off and, like with taking control? I guess because even if we hack it for like merely 3 to 4 seconds,
Hmm.
another person can overpower it and immediately take it back in control. So that's one thing, I guess.
Right, right. So actually, see, there are plenty of challenges, and in this method, and we have actually we have to explore those challenges and find out the solutions for those. That's what we want to do. It's not like everything is fixed and you just have to implement it. It's not like that. We have to
Right, right.
explore the things.
Implementation has to be done. So you guys are filing a patent for this, making it official, or how is it going to be?
Yeah, obviously a patent will be filed. Definitely, that is one option. Uh, Now, if it is a Indian patent or US patent or Australian patent, that is the next part. But first we need to know what can be done on the drones. We are buying few drones now, and we need few items which can be used on the drones for the hacking purpose, or I also want to create a students group who can develop such technique so that the other team cannot hack their drones. One team will try to hack uh, all kinds of drones, and the other team will try to block these hackers. So something like that. So we'll try
Right.
to work on these things.
So you're making a hacking drone and you're making a drone that can hack the hacking drone, or like prevent at least.
Yeah.
Right. That's nice. Is there any prerequisite programming languages you need us? Like, I mean, suppose if one person wants to join, what languages should we know for that?
See, actually, it depends on the module that we are putting it on. It is a completely, I'm going to give the freedom to the students for choosing the right method for implementing or embedding that code into a chip. Okay. But I guess Python will be best option, I guess.
All right.
The location is also very important. What is your location of where you are situated? But or are you free to visit the campus?
I'm a local, so that can be done for me.
Okay. Let's see how the students reply.
How many people are working on the team currently, and from which year?
See, there are many groups actually from other departments, other schools. Right now, I have only one master MTech students who is working on this project, and I'm going to hire the students from the other schools also. I think last trimester or last year, there was a group selection process happened for the drones. Did you know about this?
I didn't know about the drones part, but I did know that I think last year something Omni was a project that MIT started, the oxygen condenser thingy for Corona.
Okay.
So I heard about that, but I haven't heard about the drone part yet.
Okay. So I'm looking for the students right now. There are no other BTech level students who are working with me. So that's the thing. That's the status right now.
All right, sir.
Okay.
Yeah.
So see you, Sriraj.
All right, sir. Thank you, sir.
Cheers. Thank you. Bye. Shambhavi.